Okay, so we have section 3.3, increasing, decreasing, and the first derivative test. So a graph can only be doing three things. It can be increasing, where the slope is positive. It could be decreasing, where the slope is negative. Or it can be constant, and the slope would be 0. So we have pictures of each of these, where f is increasing because the slope is positive, f is decreasing because the slope is negative, and f is constant because the slope is 0. So with example 1, we have a piecewise function here, and we want to determine where the open intervals on which the function's increasing, decreasing, or constant. All right, so if we have a positive slope, which would be this part, then that's where f is increasing. So f is increasing, on -3 to 1. F is decreasing where the slope is negative, which would be 3 to 5. And then f is constant where the derivative is 0, and that would be on 1 to 3. All right. So you can read that note on the bottom if you'd like. So the only place where a function can change the slope sign would be at a critical value. So remember, that's where the derivative is 0 or undefined. And if f is a discontinuous function, the slope can also change signs at discontinuities. So we have this example 2. We have a polynomial function. So it's going to be continuous everywhere. And we have to determine where it's increasing or decreasing. Well, the only places it's going to change are at critical values. So let's find them. All right, let's hope this pen works a little better. All right, f of x is this. Oh, that looks awful. Let's try again. Oh, wow, look, that magically appeared. All right, so we take the derivative. We're trying to find the critical values. So we're going to set our derivative equal to 0 and factor. So it looks like that would be at x equals 0 and x equals 1. We'll put those on our number line. We have our x values on the bottom, and we have f prime on the top. If you plug in a number like -1, that would be positive. If you plug in a number like a half, that would be negative, and then positive over here. Come on. All right. So if we look at our areas where the derivative is positive, that's where f is increasing. So f is increasing, and focus more on my words, not on my writing. I don't know why my stylus isn't working that much. F is increasing on, there we go, negative infinity to 0, and also from 1 to infinity, since f prime is positive on those intervals. So f is decreasing on the intervals from 0 to 1, and that's because f prime is negative on that interval. All right, so that leads us to the first derivative test. And that's where we're looking at the sign changes of the first derivative. If the sign changes from negative to positive, that means our original function f is decreasing to increasing. We're going to have a relative minimum there. If f prime changes from positive to negative, f would be increasing to decreasing, so we'd have a relative maximum there. If it doesn't change signs, then it's not a relative min or a max. All right, so here we see some pictures similar to what I just drew. F has a local maximum because f prime changes from positive to negative. See, it's increasing and decreasing. Okay, f has a local minimum at x equals c because f prime changes from negative to positive. Here there is no min or max, local min or max, because f prime is positive here and also here. And f has neither a local max or min because f is decreasing on either side. Okay, so the important thing is being able to answer these and write them out in the correct way. A lot of people forget the justification part, but that you'll lose all the points for it if you don't justify what you're doing. So let's look at example 3. Find the open intervals on which f is increasing and or decreasing and justify. I'm going to try a smaller pen, maybe this will work. All right, so we're going to need to find the critical values. We have a polynomial function, it's continuous everywhere. So if we take the derivative f prime of x, yeah, that looks like f prime, right? We have 2x to the fourth minus 7x cubed minus 4x squared. That's a minus 4x squared. Ay, ay, ay. All right. So factor that. Let's see, we could take an x squared out. We get 2x squared. So 2x squared minus 7x minus 4. We can factor that. And that would factor into 2x plus 1 and x minus 4. So we have 3 critical values we're going to put on our number line. We have negative 1/2, 0, and also 4. These are the x values, and we're checking the sign of f prime. Okay, so if you plug in numbers on either side of those, you'll see it goes positive, negative, negative, positive. So if we're trying to find the open intervals on which f is increasing or decreasing and justified, f is increasing on negative infinity all the way up to negative 1/2. And it's also increasing on 4 to infinity since f prime is positive on those intervals. Okay, then we have f is decreasing, and you should be writing more than I'm writing. Write what I'm saying. F is decreasing on the intervals from negative 1/2 all the way to 4 since f prime is negative on those intervals. Now we can use our sign chart and our analysis here to help us determine where the local mins or maxes occur on this. So we have our chart up here. So as f increases and then decreases, there's going to be a relative max. So f has a relative maximum value at x equals negative 1/2. And then over here, f prime goes from negative to positive at x equals 4. So that means we have a relative minimum value at x equals 4. Since f prime changes from negative to positive. And that's the justification part. All right, last example. We have to find the relative extrema of this function and justify it. So we need our critical values. Take the derivative, 1/2 x minus cosine x. Figure out where that equals 0. So where does cosine equal 1/2? And remember, we're on the interval from 0 to 2 pi. So that would be at 1/3 pi and 5/3 pi. That's what goes on our number line. 1/3 pi and 5/3 pi. Those are our x values, and we're checking the sign of f prime. So if you plug in numbers, you should get negative, positive, negative. Tell me if you don't. So that tells us we need to find any values of relative extrema. So f has a relative min at x equals pi over 3. Now this says find the exact values of the relative extrema. So we're talking about what is that that value. It doesn't say where do these extreme values occur. It says what are the exact values. So I'm going to change this just a little bit. F has a relative min of, and what is that minimum value? Well, we need to plug pi over 3 back in to f of x. So f of pi over 3, that would be pi over 6 minus, and then sine of pi over 3 is square root of 3 over 2. Okay, so it has a relative minimum value of pi over 6 minus square root of 3 over 2. Sorry if you can't read that, but it's square root of 3 over 2. And we can say, why not throw it in at x equals pi over 3? Since f prime changes from negative to positive. Trying to save you on the writing here because you can't read my writing. All right, now we have another thing occurring here. F has a relative max at, and now we need to plug in 5/3 pi. So a relative max, oops, not at, of, and that would be 5/6 pi plus square root of 3 over 2. And that value is occurring at x equals 5/3 pi, since f prime of x changes from positive to negative at that value. All right, that wraps up this video. So we'll hopefully get a little clearer on my stylus over the next couple.